Bismillahirrahmanirrahim. Today, inshallah, we should talk about proving right triangles congruent. That is, previously we talked about proving triangles using side, side angle, etc. Those postulates and theorems, they apply to any triangles. Right triangles, of course, are a type or a subcategory of triangle that are very special because they have a right angle. So this is a exceptional category, but all the previous postulates and theorems also apply to right triangles. There's really only one new theorem here that we have to learn, and that's this one that I've presented before you over here. It's called hypotenuse leg theorem. And there are three other theorems that are mentioned in this section in your textbook, which are really not new once you analyze it. It's just a reformulation of the previous postulates and theorems, the side angle for right triangles. So, in other words, there's only one new theorem that we have to learn in this particular section, and that's this theorem right here. So what I'd like to do here is first understand this theorem and go back and add to this knowledge from regarding the other theorems that I mentioned, and do some example questions. So the one new theorem is hypotenuse leg congruence theorem. That is, how do we prove right triangles to be congruent using this particular theorem? So the name of the theorem is hypotenuse leg congruence theorem, or shortly HL. So this is HL. It basically states that if you have two right triangles and you know that the hypotenuse of the first triangle is congruent to the hypotenuse of the second triangle, and one of the legs is congruent, then the two right triangles are congruent to each other. So more formally stated, it is thus: if the hypotenuse and a leg, if the hypotenuse and a leg of one right triangle are congruent to hypotenuse and a corresponding leg of a second right triangle, hypotenuse and a corresponding leg of a second right triangle, then the triangles are congruent. Hypotenuse, leg. Easy peasy. Again, if the hypotenuse and a leg of one right triangle are congruent to hypotenuse and a corresponding leg of a second right triangle, then the triangles are congruent. So hypotenuse leg. So if the hypotenuse leg of one right triangle are congruent to hypotenuse leg of second right triangle, then they're congruent. So it's a very easy theorem to remember. So when we're trying to prove right triangles congruent, if you given that the hypotenuse is congruent, and if you're given that one of the legs is congruent, then you can use this theorem to prove that the triangles are congruent. So you have to be able to articulate this theorem. That is, if somebody asks you what's hypotenuse leg, you should be able to say this hypotenuse leg congruence theorem states that if the hypotenuse and a leg of one right triangles are congruent to hypotenuse and a corresponding leg of a second right triangle, then the triangles are congruent. I think that's pretty reasonably easy theorem to understand, and we shall elaborate on this in just a second. Now, if you recall, these were the four ways that we proved triangles to be congruent before: side triangle congruence postulate, side triangle congruence postulate, angle triangle congruence postulate, and angle side triangle congruence theorem. The last one was the only theorem one because you can use the previous one to prove the last one over there. So side angle triangle congruence postulates, and angle side triangle congruence theorems. So anyway, so side angle and angle side. So these were the four ways that we used before, we learned before, that you can use to prove triangles to be congruent. Okay, in this section, your textbook introduces four additional ways that you can use to prove right triangles congruent, and they're labeled HL, LL, HA, and LA. What does that mean? Well, the H stands for the hypotenuse, and the L stands for one of the legs of the right triangle. The right triangle, of course, has two legs and one hypotenuse, the hypotenuse being the side of the right triangle that's opposite of the right angle. So anyways, so the HL is the theorem that we just learned. That is, if the hypotenuse and one of the legs of a right triangle is congruent to the hypotenuse and one of the corresponding legs of a second right triangle, then the triangles are congruent. That's HL. That's what we just learned. Then there are three additional theorems. These are all theorems, LL-HALA. They are not really new because they are just reformulations, they're restatement of these over here for right triangle special case. So I don't even memorize these because you can still use all of the above. You can still use these in proving right triangles to be congruent, because right triangles are just a type of a triangle. You know, they just happen to be special, but they're still triangles. So anyway, so the LL, HA, and LA are really not new, and you could rightly just use the other ones to prove right triangles congruent. For example, the LL theorem, the leg theorem, says that if two legs of a right triangle are congruent to two legs of a second right triangle, then the triangles are congruent. So if two legs, LL, of one right triangle are congruent to two legs of a second right triangle, then the triangles are congruent. Well, that's like this scenario, the picture that's drawn here. But so the two legs being congruent. But then there's the right angles in between them. It has to be, right? Because they're legs and the angle between them is the right angle. And that's like side angle side, isn't it? It's like side angle side. So LL is really no different than side angle side. You could use side angle side, right? So why memorize another theorem? Okay, fine, cool. So side angle side for right triangles, then that works just as well. And then the other one, for example, HA, says that if the hypotenuse of one right triangle and one of the other angles, not the right angle, one of the other angles is congruent to hypotenuse and one of the other angles of a second right triangle, then they are congruent. Well, that's like angle, side, isn't it? Right? So that's this one over here. So this one was side, angle, side, and this HA was angle, side, right? So it's just a reformulation of angle, side for right triangles. And finally, this one, LA, it says that if one of the legs of a right triangle and one of the angles, not the right angle, other than the right angle, if one of the legs and one of the angles of the one right triangle is congruent to one of the legs and one of the angles of a second right triangle, then the right triangles are congruent. And that's this particular scenario. That's angle, side, angle. So this is like angle, side, angle. And this is like angle, side, and this is side, angle, side. So you can see these are really not new, so I don't even take the trouble to memorize these. I just used side, angle, side, angle, side, angle for right triangle. So we really only have to know one new theorem for this particular section, and you can use all the previous one, side, angle, side for right triangles also. So it's not as difficult as it may appear. Okay, now we shall use these theorems to do some example questions. Okay, so here's your first example, and it's a proof that you're supposed to do. It says given information. Okay, here's the given information. Given triangle PQR, that's PQR, that's this triangle. So triangle PQR and triangle PSR, that's PSR, that's this triangle. So triangle PQR and triangle PSR are right triangles with right angles, angle Q and angle S. So those are right angles, they're given. Okay, so we have two right triangles. And then it states that angle PRQ, that's PRQ, that's this angle right here, is congruent to angle PRS over here. So those two angles are congruent. So we're given two right triangles and we're given two angles that are congruent. Now we're asked to prove that triangle PQR, that's PQR, is congruent to triangle PSR. Okay, so I think we can do this. So in general, then again, you can use side, angle, side, angle, and angle, side, and then the new theorem that we've currently learned, that is hypotenuse leg. You can this is what we have at our disposal to proving any triangles to be congruent, including right triangles. Okay, so let's see which one of these we can use to prove these particular triangles. So we have angle. We have these two angles, and so can we use side? No. So how about side, angle, side? No, angle, side, angle. Well, we have two angles. Do we have a side that's congruent? We don't know anything about the sides, do we? Well, but we do have this, don't we? We have PR is shared between the two triangles, right? So can we use hypotenuse leg here? There's a hypotenuse, but there's no leg, right? Well, but we do have these two angles, don't we? Angle, angle, side, right? So angle, angle, side. That's pretty cool. Angle, angle, side. We got this. So we can definitely use angle, angle, side to prove these two triangles to be congruent. Now, if you wanted to say, okay, this is like hypotenuse and angle HA. So this is hypotenuse and angle given HA. This is like HA. But, you know, why add? Well, I clutter your mind with extra theorems, right? So I would just say this is angle, angle, side for right triangles. And that would be just an honest, legitimate way of proving these triangles to be congruent. So this is angle, angle, side, or hypotenuse and an angle given. And we can use that. So that's easy peasy. I think we can use hypotenuse, angle, angle, side to prove this, because we recognize that PR is congruent itself because of reflexive property. Then we have angle, angle, and a side. So we can prove these triangles to be congruent using angle, angle, side. So I'm not going to write a 2-column proof here in the interest of time, but I hope you appreciate that. Okay, so here's our second example, and here we're asked to write a 2-column proof for the following question. Okay, so here we may have to actually write a 2-column proof. So, okay, we can do it. Now, here's given information. Given angle V and angle X are right angles. So angle V and angle X are right angles. Okay, cool. They're marked for us, and that's awesome. And then we're given W, that's W over here. W is the midpoint of Vx. So here's Vx. So, and W is the midpoint. Well, if it's the midpoint, then these two segments have to be congruent, don't they? Okay, so we got that. Now we're asked to prove that triangle UVW is congruent to triangle VXW. Where's V? Sorry, UVW is congruent to YXW. So those two triangles. That's what we have to prove. Okay. All right. So I'm going to do. I'm going to brave a 2-column proof over here, and so I'm going to draw out the 2 columns. Now, so when you're formulating these type of you have to figure out, again, we only have those 5 ways of proving triangles to be congruent, you know what I'm saying? So let me write the statements, and you have reasons. I hope your handwriting is better than mine. I'm still working on it. So so statements and reasons. So how are we going to prove these to be congruent? So we have side, 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 angle, side. Sorry, it's not side, angle, side. So side, angle, side, angle, side, angle, and angle, angle, side, and then finally hypotenuse leg. That's it. So we have hypotenuse leg and be given right triangles. So you might think, okay, maybe hypotenuse leg. So this would be the hypotenuse, right? Do we know those need to be congruent at all? We don't know to be congruent. But every time you have something like this, you have to look for stuff that you can get like freebies, you know? So we have 2 intersecting lines, and then these angles have to be congruent because they're vertical. You know what I'm saying? So they are vertical angles. So vertical angles are congruent. If you see that, then we have our answer, right? Because we have angle, side, angle. Ta-da! So we can use angle, side, angle right here to prove these 2 triangles congruent. So angle, side, angle for right triangles is a legitimate way. So here you can say, you know, this is like this is one of the legs is given, one of the angles. So you can say this is LA for right triangles, or just use angle, side, angle. Why make life, you know, simple principle. Don't make life harder than it has to be. Why? Because it's plenty difficult as it is. So this is just angle, side, angle for right triangles. Okay, very good. So that's how we're going to do it. I mean, I think it's pretty reasonably okay. So first we write the given information. So angle V and angle X are right angles. Okay, so that's what we're given that. So angle V and angles X are right angles. Okay, so that's given. Okay, see, then we have to actually say that if 2 angles are right angles, then they're congruent. Right? So we have to say angle V is congruent to angle X. Okay, because all right angles are congruent. Okay, that's a theorem. Right? All right angles are congruent. By definition, it's a congruence angle. So now number 3. So we got that. So then we say W is the midpoint of Vx, segment Vx. Okay, this is also given information. And from here, see, we can conclude that from there we can say VW, segment VW, is congruent to segment XW, okay, from definition of midpoint, okay, from definition of midpoint. All right, we got that. So we got those angles congruent, we got this angle congruent, so we did this, and we got those, and we just have to get the vertical angles, and then we got our angle side angle, okay? So 5. So then we say angle UWV is that's UWV is congruent to angle YWX. Why? Because they are vertical angle. Vertical angles are congruent. Ta-da! And then finally, number 6. Now we got our angle side angle. Now we can just say triangle UVW is congruent to triangle YXW. Okay, and this is because of angle side angle triangle congruence. Okay. Ta-da! Angle side angle triangle for right triangle, if you can say that, but that's not necessary. So there we have it. So that's a reasonably easy proof, I think, and I just use these. I just 5 easy peasy to remember, I think. Okay. So let's do a couple more examples here. Okay, I like this particular question. Let's see. It says, given angle A and angle C are right angles. Angle A and angle C are right angles. Okay, we got that. And then you're told that segment AB is parallel to segment DC right here. So that's they're marked for us here. So it kind of looks like a rectangle, but we can't assume it's a rectangle. Okay, but anyway, it looks like it. But so anyway, so we know those two are right angles, and we know those two are parallel. Okay, then we are asked to prove that segment BC is congruent to segment AD. Wow, that's pretty impressive here. So we are asked to prove that the parallel, that this is parallel to this. That's how we're going to have to prove. That's kind of interesting. So we're not proving anything about triangles. What I thought we were doing about proving triangles congruent. But what are we like trying to prove? Segments and lines to be parallel. What's going on over here? First, if you remember, how do we prove lines to be parallel? Okay, if you have two lines that are cut by transversal over here, so we had, if you were given that these were parallel, then if you had two lines that are cut by a transversal, then you know a few things. You know that the corresponding angles are congruent. That's a postulate, right? The rest of them are theorems. So corresponding angles are congruent. Alternate interior angles are congruent. Alternate exterior angles are congruent, right? And the consecutive interior angles are supplementary. So we know about parallel lines. And there's converse of this. The way you prove lines to be parallel is that if you can say that the corresponding angles are congruent, then the lines are parallel. If you can say that the alternate interior angles are congruent, then the lines are parallel. If you can prove that the alternate exterior angles are congruent, then the lines are parallel. And if you can prove the consecutive interior angles are supplementary, then the lines are parallel, by converse of those postulates and theorems. So how do you prove lines to be congruent? Well, we got to get lines to be parallel. We got to get either one of these angles to be congruent. So either corresponding angles to be congruent, alternate interior to be congruent, alternate exterior to be congruent, or the consecutive interior to be supplementary. So that's what we got to do to prove lines to be parallel. So if we are to prove that BC is parallel to AD, we have to prove one of them: alternate interior, alternate exterior, corresponding, and all that stuff. So, well, do we see that in here? Where are those angles? Well, let's draw out BC over here. Let's draw out AD over here. And where's the transversal? Where is the transversal? Well, if you draw BD over here like this, there's our transversal. See? You see that? So I draw BC, that's this, and I draw out AD, that's this, and I draw out this, BD over here like that. And that's our transversal. And if we can prove, let's say, alternate interior angles like this, that would be alternate interior, right? So if you can prove that this angle is congruent to this angle, right? Then we can say BC is parallel to AD, right? Okay, so that's like actually what we're going to have to try to do over here, that's our goal. So that's what we're going to try to do. Now, how do we prove those angles to be congruent? So our goal is to prove that this angle is congruent to this angle somehow. Well, if you can prove that the triangles are congruent, then you can prove that the corresponding angles are congruent by CPCTC. Corresponding parts of congruent triangles are congruent. So if you can prove this triangle is congruent to this triangle, C, if you can prove those two triangles to be congruent, then we can prove that these two angles, the ones that we're looking for, are congruent by CPCTC. The corresponding parts of congruent triangles are congruent. So that's our goal. Our goal is to prove those two triangles, and then using CPCTC, then we can prove those angles to be congruent. So that's our goal. All right, fine. So how do we prove the triangles to be congruent now, right? So, okay, so first, step one, we have to prove the triangles to be congruent. So, what are we given? We're given those are right angles, and we're given those lines are parallel. Ooh. If you're given parallel lines and transversal, what else are we going to do? You have the boatloads of angles you can get to be congruent. So anytime you're given these parallel lines, you should be looking for corresponding angles, alternate interior angles, alternate exterior angles, and consecutive interior. You should be looking for that. Why else would you give that? What are you going to do with parallel lines if not that? You know what I'm saying? You're not going to build like a rocket ship. You know what I'm saying? So you have to look for alternate interior. Well, let's see. Can we look for some alternate interior? So this is parallel to this. Okay, and where's the transversal? Well, this is the transversal. Aha. If that's the transversal, then this angle is congruent to this angle because that's the alternate interior, see? So if I have this parallel line, have this transversal, then this one is congruent to this one. These are alternate interior angles. Those two are. Okay, so that's what we get from those two lines being parallel. All right, so you can use this information to get those two angles to be parallel. Okay, now what do we have? I mean, we gotta have something. We have a lot here. We have a right triangle. We have angle, angle, angle. Oh, look at this. Isn't this side common to both of those triangles? Yes, they have a shared side. That's reflexive property. So we have angle, angle, side here. Wow, easy peasy. Angle, angle, side. Got it. So here we can use we can use this as alternate interior angles. So those angles are congruent by alternate interior angles. Okay, and then this is by reflexive property. We have angle, angle, side. So we can use angle, angle, side for right triangles to prove those triangles to be congruent. And once we have those triangles to be congruent, then we can say that those two angles are congruent because there are corresponding parts of congruent triangles are congruent. And when those two angles are congruent, then we can prove that the lines are parallel, the segments are parallel. AB segment, we asked for BC is parallel to AD, like that, because of alternate interior angles. If two lines are cut by transversal such that the alternate interior angles are congruent, then the lines are parallel. That's the converse of the alternate interior angle theorem, and that's how we prove. So this was actually written as a paragraph proof. So if you were to write a paragraph proof, you would basically string the thoughts together as does. So you would string the thoughts together by saying first that if these are right angles like this, that's given, and then fact that these are parallel lines, you can get these two angles to be congruent because those are alternate interior angles, and this side is a shared side by reflexive property. We have two triangles that have angle, side. Then we can prove those two triangles to be congruent. Correct? So we can prove these two triangles to be congruent, and by CPCTC, we know those two angles are congruent. That's by CPCTC, and then by alternate interior angle converse theorem, we can get those two segments to be parallel. And that's a very beautiful question in my mind. I hope you appreciate that. If you have to think through this until you almost like memorize the thought process, because it's actually quite beautiful. And here's a last example for the day. Let's see what we have. Given KL is perpendicular to JM. KL is perpendicular to JM. That means those are right angles. That's what that means. And L is the midpoint of JM. So L is the midpoint of JM. That means these two segments are congruent. That's by definition of midpoint. And then we're asked to prove triangle JKL to be congruent to MKL. Okay, that's easy peasy. I think. I hope you see it. Maybe it's not that easy peasy. Okay, so here's what we do. So from KL is perpendicular to JM. Okay, so we're given that. So if they're perpendicular, that implies that angle JLK, that's this angle over here, okay, that angle JLK and angle MLK are right angles. That's what that means. Are right angles. Remember, this means perpendicular, this symbol means right angles, okay? So from this given information, from those that being perpendicular, from there we get JLK and MLK to be right angles. Why? Because if two lines are perpendicular, then if two lines are perpendicular, then they form four right angles. That's the definition of being perpendicularity. So from definition of the lines being perpendicular, then we get those two angles to be right angles. Because they're right angles, then we can say, see, from there we can say JLK, angle JLK is congruent to angle MLK. First, you have to say that they're right angles, and then you can say that they are congruent. Okay, so we got them to be congruent. And then from this one, L being the midpoint. Okay, from L being the midpoint of JM, segment JM, from there you get JL is congruent to ML by definition of midpoint. Okay, by definition of midpoint. And then this side is congruent to itself because of reflexive property. Segment LK is congruent to segment LK because of reflexive property. And there you have your proof that has side angle side. And by side angle side, the two triangles are congruent. That's easy peasy. Okay, so let's review what we talked about today before we finish. Today we talked about proving right triangles congruent. And I suggested there's only one new theorem here because you can still use side, 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 angle, 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 side. And the new theorem that we learned was hypotenuse. I said you can still use the previous postulates and theorems for right triangles, and that's why I don't add anything to this because it's a little cluttering your mind because they're the same postulates and theorems essentially. The only new theorem was the hypotenuse leg, and it stated that if the hypotenuse and a leg of one right triangle are congruent to hypotenuse and the corresponding leg of a second right triangle, then the right triangles are congruent. This was actually the only new theorem that we learned. Now, if you were to look at this theorem carefully, this is like angle, and then this is side and side, and that doesn't spell a very nice word, does it? So it's the only theorem that actually spells angle side side, and we don't use that, and that's why we give HL a new name. So you cannot apply angle side side to any other triangle except for right triangle. In that case, we call it HL. So HL is kind of like euphemism. It's like a disguised angle side side, and you can only use it for right triangles. So this is actually the only new theorem that we learned, and this is really only 5 ways you can prove triangles to be congruent in essence. If you know these, then you know how to prove triangles congruent, inshallah, and we shall develop on this next time. Until then, as-salatu was-salam wa sallallahu alaikum.